This is where we left off. I want to go over this. Uh, this is where I want to get going, but I want you and the DE students to know, and theirs might be in a little different place. I did put the writing tips, report guidelines, report requirements out there. Every one of these projects, I don't know what I've said on them, but I want the shortest reports you can give me because I have to grade them all. So that means you put a picture, right? Even though you look at my example project report and it does this, it's like, okay, this is what purpose, here's D flip-flops, and then I tell you what you see in table 1, and then I tell you what you see in figure 1 here, and then I tell you what you see here. That's fine. I want you to minimize this part, have all the pictures you need, but minimize this. And I'll tell you why. Because I'm going to be going like this and making sure everything's there and looks right. And if it does, then I give a grade. And if half of it's missing, I'm not going to give a very good grade. But the only time I'm really going to stop and read every bit of that is when it's not right or it looks different than I expected. Then I'm going to be reading it to find out, what are you trying to tell me here? Okay? I'm trying to be honest with you, that because I don't want you to have to put in a lot of work if I'm not actually going to read it. I mean, that's not fair. If I'm going to read it, then you put in the work.
And lab says that we want the VSDL listing. Do you want us to put the VSDL code?
Yeah. You can do that as a text file instead of an image. Okay. Now, there's something else I put out there. This example state machine design that's supposed to kind of help with Project 4, because Project 4 is a little more difficult. It kind of steps it up. But this one's even harder. It's got outputs associated with all these states. So Z is an output. Whenever you see Z, that's an output. And so here I've got the outputs and say what values they are. But what is similar about it is it has one hot encoding where only for all one hot encoding there is only one flip-flop high at a time. Okay? So that's what I do want you to do in topic or project 4 is a one hot encoding. And I show you the VHDL file that I used. It doesn't mean it would be the one that you used. And then I try to explain how all that stuff worked. Okay, that's all I have out there. It is a brief. It is a brief help. Yeah, you should be able to if I switch my role to a permitted student. This is what you guys see, and I see it, and I can get to it. Okay, so the I don't know. I didn't read it close enough, but I got notice basically from the department chair today that said that we are having a lot of issues, not only on academic integrity, but on proper, uh, what is it called? A student, basically the way students are supposed to react or act with their professors. And I forget what exactly how that's put. It's not just student behavior, but it's something similar. And so we were all asked to say something to everybody. I'm pretty laid back. Most of you can tease and mess with me. I want you to call me Steve, but there are some professors here that absolutely you must call them Dr. So and so. If you're not sure if they got a PhD, call them doctor. Okay, you don't want to make the mistake the other way where they got one and you don't. Okay, because people work very hard for those. I didn't. I just messed around on mine. But so that's why you can just call me Steve. All right. But they've worked very hard on these things, and they really deserve the respect. Okay, so treat them with the respect that they deserve. And I promise that the results you see will be good, right? You can catch more flies with honey than with shit, right? Maybe not, but huh?
Yeah, I was just about to say.
That's what they say.
Honey on the shit. Boom.
Oh my goodness.
Welcome to America.
Then, except these people have PhDs, they can see through that. All right, they can see through the honey on the shit. Okay, we went back. I showed you. This was the example when I did the design based on Xilinx, based on the schematic, and then I went back and did it with VHDL. Now, VHDL, you really don't have to go through that whole table, but I wanted to show you that if you looked at this and the other, it came out to be the same. But this was a second design. I wanted to step it up again. This one shows that the design has an input of W and an output of Z. Okay, so we haven't done one with an input or an output before. But we do have one that does the different states. So, and this one, I think I've had one version of the exam that has something like this. Okay, just to let you know. So, I don't know if it'll end up on it, but I mean, I know I've had a version that had a problem like this on there. Uh, It says the output should go high if there were two consecutive high inputs on W. So we could get 1 0 0 0 0 0 1 0 1 0, no high yet on Z. And then get 1 1. Now we got an output on Z, okay, where it goes high. It all changes are on the positive edge of the clock. That one might come at the next positive edge, but still. And then if it has one again, ooh, do we is it retriggerable or non-retriggerable? I don't say. So I guess you can decide how you want to design it. I would. I don't remember how I designed it, so I'm not going to say. So we got the specs. We know what we're supposed to do. This is what we're supposed to do. Now we got to derive the states for the machine. This is what I came up with. This does not mean it's what you would come up with, but this is what I came up with. And there have been plenty of times that I have come up with this or something like it, a state diagram, and decide this is not the way I want to do it, and I end up tearing it up and starting over again. So don't be surprised if you have to do that. I got state A. That could be state 1. I've got here that the output Z is 0. If W, my input, is 0, then I just want to sit here. I haven't seen any 1s yet, so I just want to sit here. If I see a 1 on the input, then I want to move to state B. Now, so state A says, as long as I'm state A, it says all I've seen is zeros on the input. State 1 says, or state B says, I've seen 1 1. I'm looking for the second one. Okay, if the next bit on the input is a 0, we go back to state A. 0 0 0 0 0. All the time we're seeing zeros. Even if it's 0 1 0 1 0 1, we just keep going back between A and B. Then finally, we see this. and we see that from state A we went here, and then in state B we saw another input that was W, and this is saying my output is 0. Okay, my output 0. It's associated with this state. So it's not associated with the input. That means this is, which one I say I don't like very much was mealy, right? Well, when you see, oops, let me go back. When you see this and the output is associated with a state, that's a Moore machine. It's not coming from what the transition is. If we come down and say here that as this input's changing and the output is now going to be 0 also, then it's having it's more of a Mealy machine where it's affected by not only the state but also the current input. So this is a Moore type machine. Most of them you can do as a Mealy or a Moore. Okay, so we've seen 1, 1. We've got to state B. Output still 0. Saw another 1. And so we came down to state C, and our output went to 1. It says we've seen 2 1s in a row. And then if we see another 1 on W, it stays here. And output on Z is still 1. That means this is a retriggerable circuit, right? If you had 3 1s in a row, you have 2 Z pulses in a row. So if it was non-retriggerable, right after here, we would have had Z equals 1, and then it unconditionally would have come back to state A. Okay, but that's not what we're doing. We're saying if we see a 1, we stay here. If we see a 0, we go back to state A. Okay, does it make sense? Does that kind of do what I said up in that first sheet, right? Where with the inputs and the outputs. Okay, so next we derive the state tables. And here, now we've got a present state and a next state and an input and an output. We didn't have those on the last one. The last one was a real simple one. You probably won't see many of those. This one is called a sequence detector. Okay? They're so popular they gave it a name. It's a sequence detector. So here we say if our present state is A and the input is 0, then we stay in A. If the present state is A and the input's a 1, we go to state B. That's important. If we're in B and the input's a 0, we go back to A. If our current state's B and we see a 1, we see that right here. If we're in state B and we see a 1 on W, we go to state C. It says it right there. So this is taking this diagram and putting it in the table form. I don't care which one you do first. To me, it makes more sense. Maybe it was because this was how I learned. And this is one of those things I never learned in school. This was something that when I came, that was too long ago. They didn't have state tables back, when we put everything on stone tablatures. But I was doing this. I was trying to learn how to do it with Xilinx, all this stuff at the same time on my own. I did have someone around that knew it, so I could take it to them every once in a while. But once I got to the point where I could simulate it, I could test it myself and see if I was right. So if I got to state C, if it's a 0, I go to A. That's what it says here. State C. If it's a 0, I go to A. If I'm in state C, it's a 1, the output. If it's a 1 on the input, then we stay in state C. That's what this is saying. So notice also that this output is associated with the present state. And it shows this in the diagram also. So all that, they really do match up. Okay. And on most uh, homework or tests and the exam again, I really want you guys to pay attention to 4 and 5 because, and the stuff we're doing now, this could all be the test. Now we look at the variables and try to minimize it. This is all the stuff we've done up until this point, right? We try to write equations for what we've seen and then minimize it if we can. And we look at our flip-flops too. Here we're trying to decide the number of variables we need. If we've got 2, well, then we're going to have at least 4 possibilities, whether we want them or not, unless it's one hot encoding, and then we would have to have 3 flip-flops because we got 3 states. But this is what we got. So if we're in state A and that's 0, 0, you could put 0, 0 up here if you want. And the input is 0, we stay in 0, 0. If the input's a 1, we go to state B. We've assigned a 0, 1 to state B. Now, I don't know if I do it, but okay. I think later on I will end up switching these two, C and D, because there's an opportunity for a glitch here when 2 bits are changing at once. So what I do is, there's nothing wrong with saying 0, 1, 3 are my state variables. And then I've only got the possibility of having, now when I go back to A, I've got one of those situations where 2 of them are getting reset and I might get a glitch. Okay, but again, our output is associated with our input. And you can see that these they match up with what we had before. Okay, now we decide what kind of flip-flops. I think, did I decide? Yeah, I decided on D again. We're going to have to do at least one with a JK so that you can see how that works. But okay, here we've got it. Again, D is simple because I mean, it's just basically what we've got in our next state. But here, it says, now this one is where I see a lot of students make mistakes, so please pay attention to this part. 0, 0, both of these are a 0, so D1's a 0. But here, our output, or our next state for Q0 could be a 0 or a 1. Well, that matches what our input is. So we wouldn't connect a 0 or a 1 to the input of that flip-flop. We would connect W there. Okay, remember when we did that with the multiplexers? Same kind of thing. Okay, here we've got these 0, 1 is the state for B. And so if we get 0 for the input, we go back to A. If we get 1 for the input, we stay in, or I'm sorry, we go to C. So it looks like for 0, 1, that matches this. So W should be the input to D1. And this is 0, 0. So no matter what, it's going to be a low on that. And then here, again, we go to 0. We stay in C. This looks like W. Okay, since it's different. Whenever you see one of these next state flip-flop outputs have more than one, or it could be more than one value. Here it could be 0, 0 or 0, 1. It has more than one value. Then you try to match up the one that has more than one value back up to the inputs. Okay. All right, and then we've got 0, 1 here. So that matches W, and the 0, 0 is a 0. And here we finally have C. The out makes the output go high when we're in state C. So when we have 1, 0 here, the output has to go high. Okay, so we could take, yeah, as a present state, a 1, 0, and these basically 1 and not 0 together to get a 1 for the output. Okay, so this you can look through the slides and you can see how all that works. And here we've done this before. We've got the states for our 4 cells in our K-map. We got 0 and 1. We get 0 and W. And then 2 and 3, we get W and I don't care. So I grouped them like this. That means we get, this would be Q0 up here and Q1, or Q1 up here and Q0 over here, something like that. But we get W1, Q1, and WQ0. Okay. Again, the way you label the columns and the rows doesn't matter in the K-maps as long as your simulation at the output matters or is right. Here we have W, and then this is cell 1, so there's a 0. This is cell 2, so there's a 0, and this one we don't care. And so this is our equation for D0. And we got to come up with our equation for Z. And one way we can do this, remember I had said we could add these two values together to get Z, but also if we ever had a 1, 1, which we shouldn't, it says it doesn't care. So we could just say if Q1 ever goes high, then make Z go high. So our expression for the output could be Z equals Q1. Okay, implement the design. This is what I got. Okay, it'd be a little difficult to go back, but I think we could go back and match all these. This one says to D0, we got to and W Q1 not and not Q0. So this should be, one of these should be, where's W? There's W. And it goes here. And then this one is Q1, not Q1. And then this one is not Q0. So you should be able to match all these up and see that I did this the same way. And then here, this is the expression I had for this flip-flop, whichever one this one is, and Q1, I guess, and then this is the output Z that we said could be tied to just Q. So again, if I were writing a VHDL test bench, I would just try to match it as closely to this one as I could. This was so much easier. I wish they hadn't ever done away with this. I really wish they hadn't. I really liked just being able to click on this and say 1 or 0 and not have to really think about it. It just sucks that it doesn't have this it doesn't have this available to us anymore. Okay, so here's W and Z, and I still don't know what Z should be, but here I've got zeros. So on this positive edge, I see a W. I don't see 2, right? And then here I see a W, and then here I see a W. So I may not see Z go high until here. I may see it go high here. It depends on how it looks at that particular circuit. Here I should see a 1 here and here, and then I shouldn't see any more 1s. So this one I must have done the circuit pretty good, so it went high with, well, that's right, when Q0, Q1 went high, this would go high. So there it is. There's 2 of them in a row, and that's it. So that works just the way it was supposed to. If we see 2 W's in a row, we get a 1 on the output. And here we had 2, so we saw 1, and then a third one came in, so we saw another 1 on Z. Okay, here's how I did it in VHDL. This was the first part. Then I did, this is interesting. You can, I don't know if I showed you this on the last one, but you can put a new type of variable in there if you want. In this one, I said the new type is a state type. Okay, it could have been state, but I wasn't sure if state was a reserved word, so I said state type. And then in the parentheses here, I've got A, B, and C. I'm saying that A, B, and C are the only values that that this variable state type can take on. Okay, and then I've got some signal Y, and that signal is a state type. So Y can only be A, B, or C. Okay, so the process, I look at either the clock or reset. If reset 0, then I go to A. That looks like it's asynchronous. And then else if a clock event and clock equals 1, positive edge of the clock. I notice that some of you are already using rising edge and falling edge, right? What is it? Is it rising edge and falling edge? Are you either one? It's easier to read, isn't it? Anyway, then we go by the case, and we're saying case Y. So we're saying we're looking at Y can only be A, B, or C. So if it's A, and if W is 0, then we stay in A. Else we go to B. It is so simple. To me, that is so much more simple. And I think most times I could go right from the diagram to this. Unfortunately, for tests and stuff, I ask you to give me, all the crap. What the hell is going on in that room next door?
Same thing.
Is this one really bizarre too? Okay. Is it one of them gay classes going on over there?
Probably. Similar.
There is a couple of those on campus that you might get stuck taking. Just grin and bear it, but don't grin at any of the other guys in the class. Don't. They might take it wrong way. Okay, when the state is B, if W is a 0, then the state should be A. Else, if what this should say, it should be an else if. No, else Y is assigned C. Okay, and then end that if, and then here when C, all this stuff, and then down here I finally say, I go back up to my state types and my Q's and all that, and I say Z equals 1 when Y equals C, else it's 0. And I didn't care about the outputs of the flip-flops. I just didn't care about them. So I didn't have anything about the flip-flops all through here, did I? So I don't know if what it did. If I don't know if Xilinx did it with D's or JK's or what. And this is what it came up with. And that looks pretty silly to me. They got 2D flip-flops, that's good, but they've and here's the only output. And then in the lookup table, they've got this one circuit. That's all they felt like they needed. So their circuit was a whole lot different than mine. But their input, and I tried to make this look the same, their output was the same too. This is why in the lab and on these thank you, projects, um, I just you know the neurological issues. Sometimes words just won't come out. Huh?
So you can't hear yourself think.
I'll go with that from now on, because everybody knows I can't hear anything anyway. Um, but this is why I want those to look so much alike. It's because then I can flip through your report great or quicker and go, okay, that looks just like fine, just like, and all of a sudden there's one different. I got to stop and really look at it and say, is this right or is this wrong? And I don't want to do anything like just go, it's not the same as everybody else's, so it's wrong. Okay, so we did learn a lot in that. It took a little while to go through them, but we did, I think, learn a lot there. Here, I've, how many? 54. We're not going to get through them. We might. Alternate approaches. This is one alternate approach. I say one of them is using a less straightforward assignment of state variables. I want to show you that. One-hot encoding, and you're going to need to know something about one-hot encoding for your project 4. It is one-hot encoding, right? And I did say on project 4, did I not, that I showed it to you, but I want to make this very clear, and this is the second time I've said it. This S equals 0 is with this line. It's associated with transition from A to C. There is no input associated with the transition from D to A. So that is non or unconditional. When you get to D, you go straight to A. All right? I don't want anybody telling me they never knew that, because it'll be too long, too bad. I said it a couple times. We got 3 inputs. We just did one that had 1 input. These, I think it's very important that you know those are and. S has to equal 1 and T equals 0. It's not S1 or S equals 1 or T equals 0. That's an and function on those. Okay? The outputs of the system are the flip-flops. That last one I had Z, I said was the output. I gave it a name, but it was just the output of the second flip-flop. Here, I'm saying that's what the outputs are. It's either going to show whatever you name A, B, C, or D. So if you name these 0, 1, 2, and 3, well, you can't. It's one-hot encoding. So this has got to be like, this has got to be 1, this one's got to be 2, this one's got to be 4, and then this one's got to be 8. Because that would put 1 bit high each time. Okay, so you have to do something like that. This has got a lot of work. Use negative edge D flip-flops. So you got to design it in VHDL and in schematics. And so you got to use D flip-flops. You got to show me the Carnot maps and state equations. There is a lot of work involved in this one project. This one's probably worth a lot more than just the 8 points that I give it. But also, it is so hard, I don't want to give it too many points and have it, if you mess it up, that you fail the class because of it. I don't want that to happen either. So it's a catch-22. Okay, develop the circuit, do the test bench. I don't think I had a test bench for that particular one, so I'll have to go through and just make sure that you guys have done it right. I'll have to, unless you can all agree on one test bench. I doubt that's going to happen. Write the VHDL code then. Okay. Use the same test bench, so I should see them match. If they don't, then you need to troubleshoot and find out where you've got something wrong and then figure it out. Write a report, but like I said, mainly show all these pictures I'm asking for, and then so that means you got to show me the schematic, you got to show me those tables, you got to show me the Carnot maps and state equations, you got to show me the schematic, you got to show me the VHDL code, and your input VHDL test bench and your output, and they all got to match. There's a lot going on. Five is even worse, right? Five is even worse. I'm going to be having to spend more time in my office. My wife is not going to be happy about that. Uh, but I need to know from you guys better times than the office hours I've got, because the ones I've got, I never see anybody, but I think Alex has been there once or twice, right? And you caught me when it was non-office hours, and I saw you today, right? Sushi today. Uh, Did you come by? You come by after class, but you won't let me go home. I'm going, I don't have an office hour now. I want to go home. And he's going, you ain't going nowhere, dude. And he just blocks the door like, if I touch him, he's going to get his lawyer on me and say that I hurt him or something. So I just won't do nothing about it. Okay, let's look at some of these approaches. Okay. I want to look at the one discussed in the previous topic, and that one we did. It's not. It's the one that has the sequential or finding the sequence detector. So since it was looking for a sequence detector, I don't need to worry about these. I only need to worry about these. This has already been done. Okay, this is just getting the specs, drawing the state table, and then drawing or making this table here. So the state diagram, state table, all that had to be done. So I had all this. Now, there are three possible states here. Okay, this is a more, and we said we had four possible states. The D came into the picture here. Two state variables, y0 and y1. That I called them Q0 and Q1 in the last one. Okay, so if you look back, please don't get confused. I just sometimes call them different things. So everything in here, what I was saying here, is everything's really straightforward. State A, 0. State B, 1. State C, 2. There was no state D, but with two flip-flops, we could have a 3. So everything was real straightforward. But there is nothing wrong with doing this. Nothing wrong at all. Okay, if we've got these A, B, and C, I could say it's 0, it's 1, and then it's 3. And that's allowing only one change between these two. But the problem is it's still going to be two changes there. So you might have to really think about it, to have it where I don't think we're going to have a glitch-free circuit here no matter what we do. But this was the only change I made it 3. And then that caused these two changes. That when we were in B and went to C, that was 1, 1. When we were C and stayed in C, this was 1, 1. So that's the only two changes that occurred because I did this. Okay, so then look what we have over here. We've got 0, 0. That's a 0, 0. Then we have a W. That's exactly like it was before. Here we got 0, 1. That was 0, 1. Now I messed up here. This is supposed to be W, isn't it? They're both 0, 1. There should be a W. These are both 0, 1. They should both be a W. I don't know. I think I carry that, or I don't carry it. Yeah, there they go. So I changed it. It changed these to W's. Was another um, effect of having that. So now this was the same I had for D1. So it was the same expression as before. And then, and we could simplify it like this and use 2 gates instead of 3, but it's in Xilinx. Who cares, right? We're not doing it in the lab, or even if we did, we'd be downloading it to the Spartan board. So who cares if we have 2 gates or 3? Uh, who was it I was working with when I was showing how little of those Spartan 3 chips we use? It's nothing, is it? It's absolutely nothing. How big? Like, let's say this whole paper is the Spartan 3 chip. The stuff we use, the part we use, isn't even as big as this picture. Okay, so we could get a lot more complicated than we do. We're not going to, because our brains can't handle it. Now with this, the 3 W's and an I don't care, I can say D0 is W, which is a lot simpler than we had before. So making this one change in my circuit made actually my circuit a lot simpler. It didn't have all that AND gates there. It just had D0 is equal to W. And then we look at our output, and our output's the same. When what we had before was, it should just say, I don't need 0, 0. I don't need all these zeros here. That was a mistake because I was new at doing this. The output is associated with the input. So if we had 0, 0 on the input, we got 0 there. The only time we have 1 is when we have 1s on the input or 1, 0. So it's just like we had before. We had Q1 there, capital Q1 actually. Now we got Y1. Same thing. So this is exactly what we had before. So all that's changed in the circuit is this. And that changes from this design to this, which to me looks a whole lot simpler, right? I changed these from 3 gates to 2, and then I didn't need any of those inputs. All I needed was the W, so that became a lot simpler. So what my point there is, look closely at the way that you count these. They don't have to. You don't have to always put those numbers in sequence. If you had, let's say, 15 states, then you've got to use 4 flip-flops. Or let's say it's 9 states. You've got 4 flip-flops, right? You got to do it. No, even 8, you have to have 4 flip-flops. But you got a lot of states there that aren't being used, and you can move them around anywhere in there. You can define them however you want. And that's one thing I do like about this. Okay, I did this same circuit as before to see if I got the same output as before, and I did. So I knew or felt pretty comfortable that this was an equivalent circuit. Okay, you do need to know how to do the one-hot encoding, because that's what so there's a lot in this design, or this presentation and the last presentation, that is going to help you get through Project 4. So here's, again, this. We're not changing anything there. What we are changing is that with one-hot encoding, each state, there can only be one flip-flop high. Okay, so now I have to have the same number of state variables as I have states. If If I've got 15 states, I got to have 15 flip-flops. That's all there is to it. Does it matter in Xilinx? Not even one little bit. Okay, so here they are. I could have done it the opposite, where it was 0, 0, 1, then 0, 1, 0, and then 1, 0, 0, but I did it like this. I don't know what I was thinking at the time. There may have been alcohol involved. I don't know.
I love your honesty.
This was before the accident, so alcohol was a very good possibility. And I had a group of students back then that used to take me out, and we never knew where we were going, if we were going for beer or ice cream. And I love them both. So it was like sometimes we went for ice cream, and then we have class, and then I was nice to them, and I'd grade their work, and they got all these A's. But I mean, when you take somebody out for beer or ice cream, I mean,
I tried to take
you did, and they did too. But I can't have alcohol with them.
We can go get ice cream. Yeah.
we could go for ice cream. Yeah, we could do that. Okay, let's look at this. Um, Again, we have to look at these. I can see that in several of these, the outputs of our next state variables could be more than one value. So here at 0, that makes that nice. But here at 0, 1, that's the same as W. Here it's 1, 0. That's the opposite of W, so we got not W. Same here, 1, 0. This is not W. This is 0. Way over here, we got a W. And I've probably shown this in all those other slides. I just like to explain it when I'm on one. Here we got a not W again, and we got a 0, and we got a W. And again, Z is associated with C, and because it's one hot encoding, we can just say if Y0 in this case goes high, so will Z. So our output, that's the only time that Y0 is going to go high, and so we can attach our output to Y0. It's really important to note that your output is associated with the present state. Okay? If I haven't made it clear, you got to just make sure you know that. Okay, here's D2. I got not W, not W, not W, and a whole bunch of don't cares. Because I don't have state 0 in there. I don't have, I do have 1 and 2. I don't have 3. I have 4. I don't have 5, 6, or 7. But since I do have 2, 3, or I'm sorry, 1, 2, and 4, I have to have this big setup here. Okay, so this equals D2 equals not W. Then on this one, D1, I had a couple zeros. Here's D1, zeros there. Now, remember, this was 1 and this was 2. And then for 4, we had W, and these don't cares, so that made it whatever was A. And A, I've got it as Y2. Okay, and the next one, I've got D0, and we've got W's for 1 and 2, and 0 here, so this is equal to W and not Y, or not Y2, I'm sorry. Okay? Now, again, we see that Z is equal to, in this case, Y0, whatever this particular flip-flop was. So, how is this different? In this particular case, these were the expressions I had before. 2 flip-flops, This one has 3 flip-flops. This one had, our old one had one 2-input AND gate. This one has two 2-input AND gates. It has the one inverter, but we can assume that can come off of Q not on the flip-flop. We had one 3-input AND gate here and one 2-input OR gate, and we didn't have those there. So this is a little simpler. If we were hooking it up, even if we're doing it in Xilinx and wiring it up, it still is a little bit simpler to do this. Okay, so, but we didn't really gain a lot on this particular one. There might be more, but anyhow, it should match up with everything else. And you should be able to match all this up with doing the VHDL also. Now here's Mealy. Okay, this one is a more. This is what we've been doing. So we don't ever use this output to do anything about, or I'm sorry, this input to do anything about this output. But this one, we can have that. So in that case, look how much it changes it. That changes it quite a bit. Now, and I don't care how you do your designs, if you do a Mealy or more. I told you about that one girl that did it, and no offense to her, if she heard me saying this, she knows I'm talking about her, because she's, huh? No. She knows I'm talking about her because she's the only one that ever did it as a Mealy, and I fussed at her quite a bit, and she was like, well, you're the damn instructor, you figure it out and tell me if I'm right. Like, she had a point, right? I'm supposed to know this stuff.
We're not going to do that to you. We'll let you.
Well, I didn't like her for doing that, but she was right. No, it didn't matter. She was right. It did give me an up. I already knew this pretty well, so going over to Mealy was not too bad. Let's see if we can figure this one out. We have plenty of time. But it's real, should be real clear, this difference. Here I've got Z is associated with A. Here I don't have that. I've got Z's associated when we've got W as a 1. Right? Here I've got Z is associated with W's a 1 and it's in state B. So that does help a little bit. I've got to be in state B and W has to be a 1. And but we don't need a state C anymore. Now if we see a 0, then output goes back to 0. So it simplifies things a great deal. All right. Here's the new state tables. This was the old one. This is the new one. I only needed one state variable. This is a good example on, see here where Z, I should have only had 1 0 here. I'm always wondering about you guys. You're not as bad as one student I used to have. I'll tell you about him someday. There should only be 1 0 here. It's associated with this. Only 1 0 here associated with this. 1 1 here associated with this. But then here we see something that we shouldn't have seen before, which is this is 0 when you're in state 0, but now we've got a 0 or 1 when we're in state B and our input is W. So we've got a different kind of situation here. Our output does have something to do with W now, and does have something to do with being in state B. Okay, here I've got now the output is Y0 and W. Okay, those two are gonna decide that the output's high. So why do we need a state diagram for this at all? Or why do we need a state machine for this? Well, we have to because we have to wait until we see two at a time, right? Otherwise, if whenever we saw W go high, we'd make Z go high. But we have to wait and let one of those W's be a 0, and then the next one that be, or when we get a 1, we got to let it go by, but we have to remember that it was a 1. And then we have to go on to the next one and see if it's a 1, and if it is, then we've got to let the output go high. You could have a sequence detector that has two variables, right? So that if, let's say, the inputs were R and S, and if R went high twice in a row and S was low twice in a row, then it should go high. So it'd have to be both. And that would get a little complicated, but you could do it. I mean, it's just, but this is what makes it a state machine. You have that part of it that it has to remember. And this, in this case, it had to remember that there was one W that was here, and we're looking for the second one. And when we see the second one, then we can let the output go high. Okay, so here's the circuit that we have for the mealy. It is so much simpler than what we had before, right? This is all we need. And one flip-flop, one D, here's W. Uh, so we connect W to the input. We have W also connected to the output with the output of this flip-flop ANDed together. That's it. Pretty simple. And that was the argument that that student used all the time. And I think in that last one for the vending machine, she took it from where most students were at about 35 states. I think she got it down to like 20 states or something like that. It, it was, and what can I say? She did a pretty good job on it. Okay, here we got the VHDL code from the previous topic. It did what it was supposed to do. You know, the other approaches, we've got this. So we could develop our code a little bit closer to whatever our particular circuit was. Let's see, this model, I guess, looks more like a, I'm trying to remember what this is about here, why we've got two processes. I can't remember why this, I can't remember why that is. So this first process, let's see what it says here, is the input logic circuit, and then the second one would be the outputs of the register circuit. It's either way. If it does the job, that's all we really care about. Here's another approach. We got signal Y for present state and or signals, and they're Y present state, Y next, and say that it's a standard vector 1 down to 0, so there are 2 bits on these, and then there are constants A, B, and C, and this shows those values. We haven't done anything like that before, but I think the way we did it before, where we said that we created a new type, was easy enough. Okay, and here's the mealy. It shows the, you can look at this and look this over, and you can see with these two processes uh, how they match up. This one, let's see, somebody borrowed a book from me. When am I getting it back?
Whatever you want.
Because you wanted a book too.
I'm good for the moment. I asked you.
You're good for the. Okay, you guys are keeping track of that. Okay. Uh, this is a pretty good book. In fact, this one's the one that, from what I've seen across, it is probably one of the more popular books on digital design in most College of Engineerings across the states. So anyway, there's two versions, one with VHDL and one with Verilog. So even these guys separate the two. It's like choose your course. You want one with VHDL or you want one with Verilog. And I think it's a good thing to do that. And here they got the VHDL. I did put this in. I was a little surprised. It didn't work. That's why I wrote that in there. So everything you see in a book does not necessarily, just because it's in a book and written, doesn't mean that it's right. I don't believe I put in anything wrong. I think I put it in right, but I could have done it. I changed it around a little bit and did this, but then I'm not sure this is really a milling machine anymore. But anyway, it did work. It was what I did to create it. Okay? I don't think I've let you guys out early ever. Have I?
No.
Never?
Never.
How many times have I canceled class?
Once.
Twice? Once?
Maybe once, yeah, maybe once, yeah, I'm sorry. Yeah, I think about it.
Last year.
Okay, get the hell out of here before I change my mind.